shifting it down here.
Oh, okay.
So we talked about self-balancing trees.
Yes.
And we went to the Wikipedia page for self-balancing trees, and there was like multiple different implementations. Uh, um, like there's like AVL trees,
Yep.
weight balance trees, red black trees is probably the most famous. I'll do it like that. Oops. I tried to only make that red. I can't. Okay. That's okay. All right. So we won't dig into too much detail. I'm gonna venture to say that all of them do the same thing when it comes to number 2.
Okay.
We talked about how they detect when the tree is out of balance last time, like
Yes.
very, very briefly, and we drew these weights. But this time we're gonna talk about step 2, which is how do you fix it when you think the tree is out of balance. And that is tree rotation. So let's say you have a tree. Zoom in a little bit more. Okay, you have a tree, and it's like 5. Then number 3, 1, 4, 7, 8. Maybe just like this.
Okay.
So it's out of balance. So this tree is out of balance. We can clearly see it. I guess it doesn't matter too much if their 8 has children or not. In the simplest case, we're gonna say it doesn't. So we're basically gonna pivot the root of the tree. We're gonna rotate, and we're gonna say because the tree is too heavy to the left, we're gonna rotate to the right
Okay.
and make the left child of the root the new root. Okay, so what that's gonna look like is this. I'm gonna promote him to becoming the new root. So 3 is the new root now.
Okay.
And 3 is and we this is might be hard to conceptualize in real life, but the former child is now the parent of the former parent. They reverse their relationship.
Okay.
But now there's a problem because now 3 has 3 children, 1, 4, and 5. What are we gonna do about that? Well, okay, that's actually easy because we can be guaranteed that 5 used to have 2 children, 3 and 8.
Right.
But we took away its left child because that its left child becomes its parent now. So we're guaranteed that 5 will not have a left child. So we just put 4 under there.
Okay.
And
That
then
makes
this
sense.
and then this just worked. It's everything about this tree is still valid. It follows all the rules of the prerequisites for being a binary search tree. And we just we rotated the tree to the right. So that in this case, it didn't help that much because now we're like too heavy to the right.
That's what I was about to say. I was
Yeah.
like, what was the point? But is it just because this is like a small example, like typically this actually would make a big difference?
Well, I mean, it's not a big difference. It's just okay, maybe I should have done maybe let's try again. Let's try again and say let me think. So we're gonna have under 1. Okay, under 1 we're gonna have 2, and then we're gonna have -1. I guess like if it like in that case it wasn't like too out of whack. You see. Maybe if we somehow started in a state there where doing a rotation will actually end up with a balanced tree. How will we do that?
Could we do we need to have it be much more lopsided on one side?
No,
Like,
I don't think so. I think it can just be very small.
okay.
Let me think. I just need to imagine like if you rotated it. Like if I rotate it, maybe I added too much stuff. Okay. Like if I rotate it back to the left now, it'll
Right.
just be too heavy on the left again. So I think what we want is we want to add more children to the right side of the tree to get the scenario we're after. So let's say we have 7 here. And we have 10 here. Okay, so now we're gonna rotate it to the left because the tree is too heavy to the right, which means we're gonna promote 5 to become the root of the tree. And then 5 is gonna be the parent of its former parent.
Okay.
And then we're gonna, I think I can do this. Yes, beautiful. Like these just followed 5 up.
Okay.
And then magically
Place 4.
we place 4 here, I believe.
Yeah. And then it's perfectly balanced in this instance.
Yeah. So that's a better example of where it actually helped the balance. So yeah, that's basically what it is. Rotation. Like you should try to doing this by hand a few times.
Yeah.
And the code. So let's try to actually write this algorithm. So the function. Let's say we had a function called rotate right, and you're given a root. Move these away. So what do you do here? What is this? How do you do this thing?
Are you given the root that you're passed? Is that the
Yeah,
current root or the new desired root?
it's the current root. So
Okay.
so for example, if I were to rotate right on this tree, the root would be 5. And rotate right would mean I want 3 to be the new root.
So does the function have access to the whole tree or just the root?
Well, by having the root, you actually do have access to the whole tree.
Okay. Okay, I'm just thinking.
Mm-hmm.
So by having the root, you have access to the whole tree. Okay. So
Because you can traverse it if you needed to. In
gotcha.
case you probably only need to deal with it at 1 or 2 levels deep.
Okay. So first, you're gonna take your root and remove it from its slot, or I don't know what the correct verbiage is, but remove it from its, is it a leaf or a node? But in doing so, can you just remove the root, or does that collapse the whole data structure?
When you say remove,
Like delete it.
you wanna pick it out of the
I want to
tree.
delete it and then hold the value of it in memory. Like make note of.
Mm-hmm.
I think I don't know. I'm just sort of talking it out
Right.
here. Stream of consciousness.
Yeah. So if you remove it, then you can remove it, but I think the thing you kind of wanna keep track of its children probably.
Yeah, so maybe
Because
removing it isn't the right thing,
I
because then
mean
you have a lot to keep track of.
well, I mean you can create a new node. Well, let me see. I don't know if at the end you actually end up removing any nodes. And at the end you end up with the exact same number of nodes. Because you're right, we're not adding or deleting any nodes.
Sure. Yeah.
So
I guess my
it's
thought process was to remove it and then immediately replace it.
yes. I mean you can think of it that way. That like let's say we do that, and then what? Like we
And
have
then
maybe does
we're
that
gonna,
also mean we're gonna sort of delete these links, and then we have like 2 orphaned subtrees like that?
yeah,
Okay.
maybe so.
Okay.
But then we have to build it back. So
Mm-hmm.
we know we're rotating right. So we're going to take the left child of the previous root and bring it into the root position and say, hey, you're now the new root.
Mm-hmm.
But then you've got these abandoned children that are just sort of floating out here. So I don't really like this method. I don't think that this is
you could
really.
you could just say, hey, you're the positioning in the diagram doesn't really matter in abstract terms. So we can just say, yeah, you're the new root now.
You're the new root.
And I think is valid to do that. Let's see. And then the other subtree, let's say, oh, come on, let me select it and move it. Okay. Okay. It's hanging out over here, let's say. So now what do you do with this?
So now 5 needs to be the right child of the new root because they've swapped. Wait,
Yeah.
hang on. Am I thinking about that right? They've swapped places.
Yeah, you're right. Yeah.
Okay, so it now needs to be the right child. So we
Right.
need
Should
to.
you just take 4 away and put it there?
Yeah,
Mhm.
but here's the thing I'm thinking about though. It's like this is all easy to do when we're just looking at it on a piece of paper, doing it by hand.
Yes.
But when I'm thinking about actually writing this as a function, this that we're talking through, it requires like so much. It's going to be so many variables of like, okay, now this is over here, and what was this value, and what was it originally? Like, it seems really messy, and I don't like it.
Okay. I agree. Yeah, it could be kind of hard to put your mind around it. But I guess my experience is, yes, it's kind of messy the first few times you do it, but once you really get it, then you can actually write an elegant solution.
Okay.
The same thing I was saying last time. I was like, to find an elegant solution is actually very difficult. But then, yes, you can recite the solution back. That also doesn't necessarily mean you totally understand it. But okay. So
Okay, we'll just keep going with the mess.
Let's do this. Let's start over.
Okay.
Let's start over. Maybe in this case we can. Okay. Let's start over, and we're doing right rotate. So 3 is gonna. Let's delete this stuff for now, just to simplify this picture. Let's delete 7 and 10. And then so we after we rotate, it'll be unbalanced to the other side.
Okay.
So now let's think about what variables we might want to use. Well, obviously there's the root.
Yes.
I'm gonna call this the root. Let's just for convenience sake set up left child and right child variables.
Okay.
I just call it left for short.
Sounds good.
Due to diagramming. Due to real estate. And then this is right. So, so I guess what we could do, like I just want the root to be, I just want to swap left with the root, right? I could write.
That would really be the first. Wait. Do we want to swap? We want to put left in the root variable.
Yeah, we could just say root equals left, and then now root is the left. But that's not enough. And that would be a problem, because we would have forgotten what the original root was if we did that, and we still need it.
So we should probably first set original root equals root.
Sure.
And then root.
And then root equals left.
Okay. Yeah. So now we've preserved both values. And the 3 is in a correct spot. It's in the root spot now.
Now, so, all right. So we're going to say, I guess what we have done is that original root is also pointing to 5. But now root is actually pointing to 3.
3, yeah.
It's cool. The arrow will move when I move the
nice
thing. How does it figure that out? That's pretty slick. Okay. Maybe I move this guy over here. So yeah, we still know what the original root is, and then we just said the root is now 3. Okay, now what do we do?
Okay, so now, let's see. Now the root is 3. So now we want to grab our value, preserve our value from right. So we maybe want to say like original right equals right. And then we want to set original root to right.
And then we want to say set original root to right.
Wait, hang on. That's what I thought, but maybe I'm trying to visualize it all.
We want to say, what are we what are we trying to do with right again?
Well, oh wait. Original root should be set to left because they've swapped places.
Yeah, original root should. Wait.
I'm
You mean
confused now.
the right of left? You want 5 to be the right child of 3, right?
But it's greater than 3, so it can't be the right child. Or sorry, it can't be the left child.
Yeah,
yes, I want it to be the right child.
Yeah,
I want 5 to be where 8 is and 3 to be where 5 is.
But 5. No, you want 5 where 4 is.
Okay, I'm confused again.
Okay.
Because I want 5
where
where 4 is. Okay.
Because you want 5. Well, okay. I mean, we look at, okay. Depends on how you think about the operation, I think. But like maybe we were thinking about, oh, this guy can rotate, but if we, but that's actually maybe not the right way to think about it. Maybe that's misleading. And instead of thinking about this line rotating to the right, maybe we should think about it as we took this whole thing. Oh, can I select multiple? Command click? Shift click? Oh, shift click. Okay. Think about shifting this whole side, so the whole right side of the tree, including the root, shifting it down here.
Oh, okay.
Maybe that's that way maybe helps more in writing the algorithm. And we're gonna replace 4 with this whole thing.
I like that better. That's easier to wrap the head around. Yeah.
Yeah. At 4 you gotta go, and then we're going in here. Okay. That's what's happening. So, how what let's start over.
Redo this. Yeah, I like that. Okay. So basically, we just want to say we want to cut out the root and its whole right side into a chunk, and then remove 4, hold 4's value, and stick the subtree chunk there, like insert it.
Yeah.
And then we just have to figure out what we're doing with that left child of the new root. So it's like we hold the value, we find our new root. We're like, okay, we have our new root. We take it the value of its left child and hold it somewhere. We
you mean the right child? You mean 4.
Yes, I do. I'm sorry. My left-right, my left-handedness is getting me again.
Yeah, just say the 4. The 4. Yeah, we're gonna hold 4.
We want to hold 4.
Yeah, and then kind of take 4 out, really.
Take 4 out, yeah. Like basically delete it, but we want to preserve its value.
All right.
And then we want to take our subtree that we've sliced out and move it into 4's previous spot.
Or the original tree, original root, kind of.
Exactly, original root.
We want to move it here.
Yes.
Yeah.
So now we just have 4 to deal with. This is good.
Let's do okay. So how would you write that in code? Maybe like step 1, preserve the 4. Yes. How do you preserve the 4?
So step 1 is actually, we're given the root. We want to find its left child, so we know what the new root is going to be. We know where our starting place is. So we have to define new root first. So we're
isn't that just root?
But root, I thought root was 5 at this point.
No, we changed root to the left.
Oh, I see. Okay, we didn't get rid of that. Okay, okay. We already have those 2 lines. Okay, you're right. So now we have root. Okay, so now we want to say root right child delete. Well, before we delete it, we have to store it in a variable. So we have to be, I don't know what to call it.
The root that, yeah, what do you call it? Maybe say, this is a, I don't know what to call it. Right,
It's gonna be
right
an
of
orphan
left.
delete.
Okay, orphan. Okay.
And then we'll have to figure it out at the end, but we just have to preserve it.
Leaf.
There we go.
Leaf. No. Orphan leaf is, I don't want to write too long because
Sure.
real estate. Okay. Or just call it orphan. It's an orphan. Is the root right? So that would be 4. So we're gonna say orphan is this 4.
Okay. And then we're going to delete it. We're going to delete root right because we have to make room.
Okay.
There.
So it's kind of like setting it to null or something, or
Yeah.
you could, and I guess in JavaScript you could also say, let's go to the null.
Yeah.
I will do that.
Set it to null. Yeah.
All right. So now that means we have this guy can come out here, and then yeah, I'll leave this line here so that later on it can. So all right. Now what?
So now here's the big question mark in my mind is there some mechanism for slicing a tree? Like it seems like there should be. Like I want to take 5 and all of its right subtree and hold that, like I want to hold that all together. I want to preserve that subtree so that I can just plug it in. But I don't really know how to do that. Like how to write the pseudocode for that.
No, there's nothing to do to achieve that because the tree is already attached to its children.
Okay.
So there's nothing you need to do to say move this tree and bring along all of its children. It will by default bring along all of its children.
Okay.
Because it has pointers that's pointing to the children, and unless you unset those pointers, the children will come with it.
They're automatically grouped. Okay. Unless you actively remove them. Okay.
Mm-hmm.
Cool. Well, so then the next step would be to get the value that we stored in original root in the very first step and to set root right of 2, 5. To a root right equals original root.
Okay, root right equals right. So now this is exciting. We're gonna do this.
Yep.
Except we still got this little line here.
Yeah, that's kind of good.
So this, what is this? Now I didn't draw the arrows initially, but maybe in this case I should draw the arrows because originally this line was pointing this way, and then this line is pointing this way. Okay. Okay. Well, okay. We actually previously we didn't talk very much. We didn't write out the algorithm for every little thing. We wrote the pseudocode kind of, but not in this level of detail. Maybe I'll give you an exercise to do that later. Implement these things. It'll be fun. Like on like when you have some free time. I don't know. Try to work on some of these algorithms. I think you'll enjoy it. But I guess the point of these arrows is to say it's the root that's pointing to the child, not the other way around. And usually that's how trees are implemented. Although there are some implementations of trees where they both can point to each other. We're not gonna do it that way. So which means if we're gonna move 5 down, oh, I love the fact that the arrow follows me. This is so cool. So if we move 5 down here, actually 5 still thinks 3 is its left child. And we have like a mutual contradiction here. Like 3 thinks 5 is its right child, but 5 thinks 3 is its left child. So we need to break one of those links, I think.
Yeah, that's what I was kind of getting at when I was thinking about slicing 5 and its whole right subtree out. So then we would be left with like 2 small subtrees that we could rebuild.
By right, did you mean left?
Okay. No, because I was thinking 5 and 8 as its right child. They need to be this sort of. They need to be cut out. The link needs to be removed between 3 and 5, and then we would just have 3 with a left child of 1, 5 with a right child of 8, and then 4 hanging out there all by itself. That's kind of the state I want to get into, so that we can rebuild.
Okay, let's do that. Hold on. Okay, so basically you want these guys by themselves.
Yeah, like the link between
like
3 and 5.
You just want to sever this link here.
Yep.
First.
Exactly.
Okay. All right, let's write the code to do that. How do you sever this link?
So I think we might need to back up a step. Let me see. Root, we've set root right to null. No, we wanted to do that because that's removing the 4. 4 is stored in the orphan variable. Then we set root right, which is the right of 3 to null. We want to do that. Okay, so we need to get rid of that last step. Root right equals original root, because there's things we have to do before we can do that.
Okay.
So in between the last two, like in between, can you see my?
I'll just insert another line here.
Yeah.
Yeah, I can see your arrow now.
Yeah, here.
You can type too, I think.
Oh, can I?
You can edit this as well. Yeah.
Oops. Oh, there we go. Yeah, I sure can. Okay, so in between these two steps, we want to, and I'm just making up words here because I honestly have no idea how this actually happened, what the mechanism in code would be to do this. But we want to like slice the tree. We want to take 5, the node. Okay, so we want to say original root, like slice, but that's probably not what it really is. But
you just want to unset its left child, really.
Unset original root's left child?
Yeah, like the same way we unset 3's right child, 4, and take 4 out. Okay. We can just do the same for 5 and take its left child out. Similar to this line here.
Okay, so but it's no longer root, it's original root now. So we want to say like original root dot left will be equal null.
Yeah. So that means, or I just keep to the same way I was doing it visually. That would mean it's not pointing to anything anymore.
Okay. So now we have exactly what I was saying. We have 3 is these are like weird little funny trees. 3 has 1 child, that's 1. It's 2, it's right.
Yeah.
To its left. And then we have 5, it has 1 child, and then we have our orphan 4. So now we're ready to rebuild. I think these 6 lines of code are, hey, let's take this thing apart.
Yeah.
And now
we also did this one, which is root that right is equal to ordinal root, which we did that already. So that line will make this whole thing be pointed to by 3.
yes,
as its right child. So we're already here.
We're already
so
here. Okay.
We're
Yes.
we're only one step away from doing
So
it.
now we have to deal with our orphan.
Yep.
So, okay. So programmatically, what we said this at the beginning, that we know that we're going to have a null endpoint to the left of what was the original root, because we've just removed, like, we can know that that's where our orphan always should go.
Yeah, the reason now that we wrote out the code, the reason we are guaranteed that this original root will always have a room on its left side is because we set it to null right here.
Right.
And we set it to null ourselves. So
that makes sense. And I guess then the other question is, how do we know? I know we do know, but how do we know? How can we ensure that our orphan is always going to be greater than our original root? So it can always, go on to the left child.
Well, because it used to be the right child of 3. And that guarantees that it's greater than 3. It used to be here.
Right.
And by the rules of binary search tree, it says your right child must be greater or equal to you.
So, okay, so we know that, but then our original.
But it has to be less than. It has to be less than the original root as well, right?
Right. It has to be less than the original root.
In this case, we can see 4 is less than 5. But in general, we know that's true because it used to be like this. It used to be like this, and this. So 4, because 4 is a part of the left subtree of 5. That guarantees, like, anything within the left subtree of 5 is guaranteed to be less than 5.
Okay. True. Okay. I'm there. I'm following. So yes, we can confidently say, like, programmatically, it can always go there. We know that will always be true. So the last step is just to set, or let's see, what's the variable now that's identifying 5? What's 5?
Original root.
Original root. Okay, so we're gonna say original root. Here, do it.
Okay.
Right spot. Okay, we're gonna say original root dot left. Wait, is that right? Yeah, left. Equals orphan.
Are you writing?
Yes. Can you see?
Hold on. I don't see your. Oh, now I do. Okay. Cool.
Yeah.
Original root dot left equals orphan. Yeah. Yes, that puts it there, and I think that's it. I believe that works.
That's actually not as messy as I thought it would be. a little. It's a lot of steps and a lot of switching around, but it's not too bad.
Yeah. Yeah, I think that works out, and it's kind of like a neat exercise. It's a neat coding exercise, I think. I wonder if they have it on LeetCode. Let me look it up, actually. Go away, bar. I can't make this bar go away. Okay. Oops. All right. Delete code. Tree rotation. Tree rotation. Invert a binary tree. No, that's not what I want. Rotate function. Oh, they don't have a problem for tree rotation? Okay. I'm a little bit disappointed. Okay. Well, that's cool. I mean, I would say actually there's not too much more to say about tree rotation. You would write a symmetric function to rotate it to the left. And then you just like, if you're implementing your red black tree or your weight balanced tree, then you like when it's that time you think you should rotate it, then you just call this function.
Yeah, that's pretty cool. Yeah, like so. Yeah, this was a good exercise.
Oh, hold on. Actually, I didn't talk about. Maybe there's a little bit more to say about this.
Okay.
So, when do you do this? When do you actually like in the normal operation? Like, because you're not gonna the programmer that's trying to use your usually you write a implementation of a binary search tree and then as a library, and then you let application developers use your library, and even if you are not like you're not like you could be the same person that's using the tree.
Sure.
But you still can think of it as you're taking on different roles. Like sometimes you're the library developer and other times you're the application developer. So I think it would be weird to say, oh well, the application developer sometimes has to call these rotate functions on the tree to make sure it's balanced. And also and also like it's not just you don't necessarily just rotate the root of the tree, because sometimes the subtrees might be unbalanced.
You
And
might
just
rotate a subtree.
yes, and just rotating the root of the tree might not help all that much if, say, like let's say we had that scenario we had last time where it was like just 1, 2, 3, 4, 5. Like let's say we had this, and then you're like, oh yeah, that's really unbalanced. Let's rotate the, to a left rotation, and you would end up with this. Then that's better, but it's still not great, right?
Right.
And then also if you say, okay, that's still not good, let's do another left rotation, then you would end up with this, probably.
Which that would be good.
That would be better, but still, like imagine this list was longer, like it had 100 things in it, and then you just do a bunch of left rotates, and then you would just have a very long V.
Yeah.
And that's not a fully balanced tree, and we're still not using the power of the logarithm, right? How we can exponentially increase the number of elements we can handle just by increasing one level of the tree. We're not going to get that if all we do is rotate the root of the tree, right? So we actually want to sometimes rotate the subtrees, the internal nodes as well.
Yeah. So is the question like when does this happen? Like when?
Yeah, when do we call this rotate? And so this doesn't have to be the root. This could just be any node within the tree.
Starting node or something.
Yeah. So so the answer is you do this rotate on an on-demand basis as you're editing the tree. That's how you do it.
Okay.
So like as you're adding a new node to the tree, then you check to see whether I should do a rotation or not.
Yeah, that makes sense. That's what I was kind of thinking.
Yeah, and
Like
or
baked
as
in.
you're right when you're deleting a tree and you're drilling down into some part of the tree, and then you're like, oh, deleting it. Okay, right after I delete it, let's check the balance. Should we do a rotation? Yes, let's do it. So that's generally how things go.
Just like you're constantly checking your balance anytime an edit is made.
Yeah.
To the tree. Yeah. That makes sense. Yeah.
Mm-hmm. Yeah, so that's self-balanced trees. We'll talk about the tree traversal next time.
Okay,
probably.
that sounds good. What did you want me to do as an exercise? Just if we could touch on that real quick. You said
Sure.
write out, sort of like we did today, write out the pseudocode steps for what? For something we talked about before.
So let's say I would like to, and this could be a longer term project. I don't want to put stress on you because I know you're busy at work. But maybe the project is like build your own implementation of a binary tree.
Okay.
It's always gonna have to be like that because unless you do everything from scratch, you won't fully get the experience. Build a binary search tree library. Is basically that's what it is. So maybe number one is design the data structure to hold the tree. I'll just I won't write so wordy. I'll just design the data structure.
Okay.
Number two, like just implement CRUD basically. Implement the CRUD operations. Which obviously is a big thing because CRUD has a lot of stuff in it.
Yeah.
But the important thing is the sort of binary search algorithm based on the tree structure, right? But that's just a retrieval. That's how a retrieval is usually done. Tree traversal, which we're gonna talk about next week. Okay. Self balancing, that's kind of more advanced as we talked about.
Sure.
So but let me think. Oh, maybe even some like more advanced sub-range searches. Like I have a whole tree filled with people's information, and I want to search. I want to type JEF and get everyone whose name starts with JEF, for example. Okay. That's a sub-range search of the tree. Or if the key is a number instead of a string, maybe I want to print out all the entries between 15 and 17 or something like that.
Okay. I have a question about step one.
Yeah.
I'm a little bit, I think I'm missing something. Design the data structure. Mm-hmm. The data structure is a tree. Like, what do you mean design the data structure?
I mean, how are you going to represent the tree in your programming language?
Oh, okay.
Like, what I'm not gonna even prescribe a programming language. I will let you choose. I don't care. But depending on the programming language you choose, the data structure could be very different.
Gotcha. Okay, that's what I needed to know. Okay, gotcha.
Yes. So yeah, think about, and then yeah, I don't want to put more stress on you, so you can sort of do it at your pace and as you're motivated to do it. And
Sounds
then
good.
when you have something, then show me.